In this lesson, we will discuss Taylor series. We are now ready to present an important result called Taylor's theorem, which states that analytic functions can be represented by polynomials with an infinite number of terms, which is known as a power series. So suppose f is analytic throughout an open disk absolute value of z minus z0 is less than capital R0. So this is the open disk centered at z0 with radius R0. And at each point, Z in that disk, f of z can be represented by power series f of z has the power series representation f of z equals the sum n equals 0 to infinity of the nth derivative of f evaluated at z0 divided by n factorial times z minus z0 to the power n. So this applies only for z within distance r0 of z0. So we know what it means for a series to converge, and so what we're saying is that this power series converges to f of z when z is in the disk centered at z0 with radius r0. So a couple of notes about this power series. First, the power series above is called the Taylor series of f of z. Centered at z0. And with the agreement that the zeroth derivative would just mean f. So the zeroth derivative of f at z0 is just the same as f of z0. And we agree that 0 factorial just equals 1, so that the formula works in the case when n equals 0. Third note, it's often useful to have the Taylor series centered at 0 because the formula becomes a lot nicer, and this is called a Maclaurin series. So when the series is centered at z0 equals 0, the series is called the Maclaurin series. We have the Taylor series centered at z0. If the Taylor series is centered at 0, we call this the Maclaurin series. So this formula is nicer. It simplifies to the sum n equals 0 to infinity, the nth derivative of f evaluated at 0 over n factorial times z to the power n. And this is valid for z an absolute value less than R0. And one final note before we present the proof of Taylor's theorem is concerning the radius R0. The greatest value of R0, so R0 is a non-negative number, the greatest value of R0 such that a power series centered at Z0 converges on the disk absolute value of Z minus Z0 is less than R0. So the largest possible value of R0 such that this power series converges is called the radius of convergence. Now let's give the proof of Taylor's theorem. So the proof of Taylor's theorem is actually a pretty nice application of the Cauchy integral formula. We're going to assume that f is analytic in the disk absolute value of Z minus Z0 less than capital R0. And we're going to choose a positive number r, little r, such that r is going to be less than R0, and we want the disk centered at Z0 with radius little r to be contained inside the disk centered at Z0 with radius capital R0. Then I'm going to let C sub r be the circle centered at Z0 with radius little r. This way the function is guaranteed to be analytic inside and on the circle C sub r, so we can use the Cauchy integral formula. By the Cauchy integral formula, we can write a formula for f of z. F of z can be written as 1 over 2 pi I times the integral over C sub r of f of w over w minus z dw. Now I'm going to expand the denominator 1 over w minus z as a power series. For w on the circle C sub r, and z is going to be distance less than r from Z0, we have the following. We can represent the fraction 1 over w minus z in the following way. I can break this up in the denominator. I can rewrite this as w minus Z0 minus the quantity z minus Z0. So I'm essentially adding and subtracting Z0 on the denominator. And I want to do this so that I can factor out the factor of w minus Z0 in the denominator. So this is going to be 1 over w minus Z0 times the fraction 1 over 1 minus z minus Z0 over w minus Z0. Now notice that the quantity z minus Z0 over w minus Z0, this quantity should be less than 1, this quantity right here, well, z minus z0 in absolute value z minus z0 is going to be less than r, and the denominator w minus z0, so w is going to be on the circle centered at z0 with radius r, so the denominator equals r. So we see that this quantity in the denominator in absolute value is less than 1, so we can use the formula for the geometric series. So we still have this factor of 1 over w minus z0, but then I can rewrite this large expression in parentheses as the series n equals 0 to infinity z minus z0 over w minus z0 to the power n. And I can bring in the factor of w minus z0 into the denominator, and so we have that this equals the series n equals 0 to infinity z minus z0 to the power n, and we have w minus z0 to the power n plus 1 in the denominator. Now I'm going to substitute this power series for the fraction 1 over w minus z in the Cauchy integral formula above. So then we have f of z equals 1 over 2 pi I integral over CR. I have f of w times the series going from 0 to infinity, t minus z0 to the n over w minus z0 to the n plus 1 and dw. Now I'm going to use the fact that if z is within the radius of convergence of z0, that the series, the power series, actually converges uniformly to the function f of z. We're going to need this so that we can, in order to switch the order of integration and the infinite sum. So since the series converges uniformly, for z within distance less than distance r0 of z0, this enables us to actually switch the integral and the infinite sum. So this enables us to write f of z as the sum going from n equals 0 to infinity of the integral over CR of f of w over w minus z0 to the n plus 1 dw times the factor z minus z0 to the power n. But if we recognize this expression right here inside the circle by the general Cauchy integral formula, we recognize this as the nth derivative of f evaluated at z0 divided by n factorial. So by the general Cauchy integral formula, we recognize this as the sum n equals 0 to infinity of the nth derivative of f evaluated at z0 divided by n factorial times z minus z0 to the n. And this again is true for all z in the disk z minus z0 less than r, where r is any value less than r0. And this concludes the proof of Taylor's theorem. So every analytic function in a disk can be represented by an infinite power series in that disk. So let's look at an example of a Taylor series. Notice that the function f of z equals e to the z is an entire function. So we can actually write e to the z as an infinite power series centered at 0. That is, we can find a Maclaurin series which is valid on the entire complex plane. So it has a Maclaurin series representation. Remember, that's just a Taylor series centered at 0. So this Maclaurin series will be valid for all z in the complex plane. So this would be a power series centered at 0 with radius of convergence equal to infinity. Now notice that the nth derivative of e to the z is equal to e to the z. So if we evaluate the nth derivative at 0, we get e to the 0, which is equal to 1 for all n. So then the Maclaurin series, defined as the series going from n equals 0 to infinity of the nth derivative of f evaluated at 0 over n factorial times z to the n. Well, the nth derivative of f at 0 is just 1, so this will just be equal to the sum n equals 0 to infinity of z to the n over n factorial. And this is true for any z in the complex plane. So if the absolute value of z less than infinity. So this is an important power series representation. This power series can be used to generate the power series for sine of z and cosine of z. Next, let's consider the function f of z equals 1 over 1 minus z. We've actually already found a power series representation for this, and this function is analytic everywhere except for at z equals 1. So we can actually find a Maclaurin series for this function centered at, so the Taylor series centered at 0 with radius 1. So if f of z is 1 over 1 minus z, then we can see that the nth derivative will be equal to n factorial over 1 minus z to the n plus 1 for all non-negative integers n. As I just mentioned, f is analytic on the disk centered at 0 with radius 1, since z equals 1 is a singularity. Of f. So we can find a Maclaurin series for f. F has a Maclaurin series representation for z and absolute value less than 1. And by definition, the Maclaurin series will be the sum n equals 0 to infinity, the nth derivative of f evaluated at 0 over n factorial times z to the n. But from the formula above, we see that when we plug in 0 into the nth derivative, we will just get n factorial. So this equals n factorial over n factorial times z to the n, and this equals the formula that we already knew, that is that the function 1 over 1 minus z can be represented as the geometric series, the sum going from n equals 0 to infinity of z to the n. So thus we have derived the geometric series again, that is that the function 1 over 1 minus z equals the sum n equals 0 to infinity of z to the n, and this again is valid for z in absolute value less than 1. So before, when we derived this expression, we started with the series and found the limit of the nth partial sums, and we found the formula 1 over 1 minus z. Now we are starting with the function 1 over 1 minus z and using the Maclaurin series to represent this as an infinite power series. Now that we have this power series for 1 over 1 minus z, we can actually make substitutions in this expression for z to get power series for other expressions. So as an example, by replacing z with negative z above, that is in the geometric series expression, and noting that if the absolute value of z is less than 1, then the absolute value of negative z will also be less than 1. We can obtain a new power series. We obtain the power series for 1 over 1 plus z. So this will equal the series n equals 0 to infinity. Now I have negative z in parentheses to the power n, so this will be the same as negative 1 to the n times z to the n. Instead of just adding the powers of z, now we have the alternating sum, so 1 minus z plus z squared minus z cubed plus z to the fourth, and so on. And again, this is valid for z in absolute value less than 1. Likewise, we could substitute negative z squared. So using the substitution negative of z squared for z and the geometric series, and noting that if absolute value of z is less than 1, then the absolute value of the negative of z squared will just be equal to the absolute value of z, the quantity squared, which will still be less than 1. We can obtain another power series representation. So now this power series for 1 over 1 plus z squared by the geometric series will be equal to the sum n equals 0 to infinity. Now we have an alternating series, so we have negative 1 to the n, but instead of z to the n, it's going to be z to the to n. So c squared to the n. So this will be 1 minus c squared plus c to the 4th minus c to the 6th plus c to the 8th, and so on. And again, this is valid for z an absolute value less than 1. So these infinite power series have an interesting property. We know that polynomials are entire functions, and it turns out that a power series is just an infinite polynomial, so it should be no surprise that it actually represents an analytic function. But it's only analytic when z is within the radius of convergence of the center of the power series. So the power series, represented by function f of z equals the sum going from 0 to infinity with coefficients a sub n times z minus z0 to the n. So this power series centered at z0 with radius of convergence capital R sub 0 represents an analytic function at each point z within distance r0 of z0. So with absolute z minus z0 less than r0, and as an analytic function, it is therefore differentiable. So moreover, this series can be differentiated term by term, just like a polynomial. So this series can be differentiated term by term. So that is, the derivative of f will be equal to the sum n equals 0 to infinity, and the derivative with respect to z would be n times the coefficient a sub n times z minus z0 to the n minus 1 power. This again allows us to generate power series representations for derivatives of expressions we already know. Let's look at an example. So we know that the geometric series can be written as 1 over 1 minus z, can be written as the series n equals 0 to infinity of z to the n, and z is less than 1 in absolute value. So then differentiating with respect to z on both sides of this equation gives us another power series representation, and we just differentiate inside the series. So this tells us that the derivative of 1 over 1 minus z, which is 1 over 1 minus z squared, would equal the series n equals 0 to infinity, and the derivative of z to the n would be n times z to the n minus 1. Now, the first term of this series would be equal to 0, so by changing the values for n, we can actually write this as 1 over 1 minus z quantity squared. We can write this as the series n equals 0 to infinity of n plus 1 times z to the n. So this way, the first term of this series is no longer 0. So by differentiating a power series term by term, we can actually find power series representations for other analytic functions. Let's look at another example of this. So now I'm going to let 1 minus z take the role of z in the geometric series. This will give me a power series representation for the expression 1 over z. So 1 over z is the same as 1 over 1 minus the quantity 1 minus z. And when 1 minus z in absolute value is less than 1, this will be equal to the series n equals 0 to infinity of 1 minus z to the n. And I'm going to put this in a Taylor series form by factoring out a negative 1 from each term. So this is negative 1 to the n times the expression z minus 1 to the n. So this is valid when 1 minus z in absolute value is less than 1, but 1 minus z in absolute value is the same as z minus 1. So when this is less than 1, then we have this Taylor series representation for 1 over z. So the Taylor series for f of z equals 1 over z centered at 1 is given by this series n equals 0 to infinity, negative 1 to the n times z minus 1, the quantity to the n, and again this is valid for z minus 1 absolute value less than 1. Now I'm going to differentiate this power series term by term to obtain a new power series. By differentiating term by term, we obtain the following. Well, the derivative of 1 over z would be negative 1 over z squared, and that's the derivative of 1 over z. And so then taking the derivative inside of the series, taking the derivative term by term of negative 1 to the n of z minus 1 to the n, we obtain the series n equals 0 to infinity. Negative 1 to the n is a constant, and then the derivative of z minus 1 to the n will be n times z minus 1 to the n minus 1. And I can rewrite this, since the first term of this is 0, I can rewrite this as n equals 1 to infinity, negative 1 to the n times n, the z minus 1 to the n minus 1. Now, the first expression on the left side is negative 1 over z squared, so I can cancel a power of negative 1, and then by replacing n with n plus 1, we can actually obtain this following formula: 1 over z squared equals the sum, now n goes from 0 to infinity, negative 1 to the n, because I canceled a power of negative 1, and it'll be n plus 1 times z minus 1 to the n. And again, this expression holds for z minus 1 and absolute value less than 1.